Welcome back to the next video, everybody. Today's video will be the last video that we spend gathering results to prove solvable n equals 2 Langland's reciprocity. Okay, and today we'll look at the fourth instance of Langland's functoriality needed to engage in that proof. That is the theory of base change. So where are we? I claim that what's left to do to finish the proof of Langland's tunnel, and hence to finish the chapter, is to prove this theorem 9 here, which says if F is a number field and we have a representation rho from the Veil group of F to GL2 of C, and that's a solvable irreducible representation, then there is a unique irreducible automorphic cuspidal representation, pi of rho, with local components pi sub b over places v of F, of GL2 of the adels of F, such that trace of rho of Frobenius at B is trace of the Langland's class T sub pi sub b for almost all places v of F. Perfect. This is just automorphic Langland's tunnel, which we already know implies classical Langland's tunnel if we restrict this theorem to the case rho is odd and factors through the Galois group of Q. So it's more general than we need in some sense. And there is a weight one condition, remember, in the conclusion of automorphic Langland's tunnel that is not present here. But remember, we discussed that it's not actually missing. It pops out for free. See proposition 2 in a previous video. And also, I should just say again, this is just a special case of Langland's reciprocity when n equals 2 and k equals q. Okay, here's the fourth instance of Langland's functoriality we're going to need. It's called the theory of base change. Let E over F be a cyclic extension of a number field F of prime degree L. Base change is trying to do the following. I want to describe the correspondence between automorphic reps of GLN of the adels of F and those of GLN of the adels of E. What's a natural way of doing that? Well, remember, we have a restriction of Galois representations of the Veil group W sub F to W sub B. W sub B just lives in W sub F. We're only going to require base change results for n equals 2, so we're only going to describe those. Okay, so what is a base change lift formally? Well, let's suppose pi with local components pi sub b is an automorphic cuspidal rep of GL2 of the adels of F. And let's let big pi with local components big pi sub W be an automorphic representation of GL2 of the adels of E, the extension field. We'll say big pi is a base change lift of little pi, and we'll write BC E over F of pi. If for each place V of F and each place W lying over V in E, the extension field, the Langland's parameter attached to big pi sub W is just the restriction to the local Veil group W sub E sub W of the Langland's parameter sigma sub B. And remember, the Langland's parameter is just a representation of the local Veil group W sub F sub B to GL2 of C. And this is the Langland's parameter of pi sub B. So what's going on here is you just have this Langland's parameter, right? Now, W sub E sub W lives here because little w lies over V. And so you can restrict this map down. Okay, but also big pi sub W just has a Langland's parameter similarly, right? Well, that's a representation of W sub E sub W. If those two representations on of W sub E sub W agree, we're going to say big pi is a base change lift of little pi. Okay, this is an instance of Langland's functoriality. If you let G equals GL2 and you set G prime equal to res E over F of G, this is the restriction of scalars functor defined last video. We already saw that G hat prime is just a product of L copies of GL2 of C indexed and permuted by the Galois group of E over F. So let's let rho from the L group of G to the L group of G prime be the natural map that takes G cross W to L copies of G cross W. What does functoriality suggest? It suggests there should be a map taking automorphic cuspidal reps pi of GL2 of the adels of F to automorphic reps big pi of GL2 of the adels of E, because that's G prime of A sub F, right? Such that what? Well, such that when pi sub b and big pi sub w are unramified, the local Langland's class T sub big pi sub w should just be rho sub v of the Langland's class T sub little pi sub b. Okay, well, it's easy to check that if pi sub b is just the representation induced by mu1, mu2 with mu I unramified characters of F completed at V, then the base change with respect to E over F of pi sub b is a representation big pi induced by characters nu1 and nu2. And what are these nu sub i's? They're just mu sub I composed the norm map from E sub w down to F sub b. And it's easy to check, although I won't go into details, that base change does actually satisfy functoriality. Okay, one other small remark, but important. E over F is cyclic of prime degree, right? From algebraic number theory, this is covered in Neukirch. We know that each place V of f is either inert, so it remains prime when you bump it up to E, or it splits completely there, meaning there's no ramification at all. And even the residual degree extensions are just one each. Okay, well, but if you're in this latter case, isn't E sub W just isomorphic to S sub V for any W lying over V? Yeah, so base change doesn't tell us anything new here. The base change lift of pi sub B is just big pi sub W, which is isomorphic to little pi sub B, right? So let's just assume we're not in this case ever. So usually, without loss of generality, we're going to be dealing with the inert local case from here on out. Okay, here's the theorem of base change. Theorem 10. Assume all of the above setup and notation. First, three things are true. First, every cuspidal representation pi of GL2 of the adels of f does have a unique base change lift to GL2 of the adels of e. Now, this lift might not be cuspidal, but it will be cuspidal unless E over f is quadratic and pi is either dihedral or monomial. Okay, these definitions were given in proposition 3 in a previous video. 2, if two cuspidal representations, pi and pi prime, have the same base change lift to E, then pi prime is nothing other, up to isomorphism, pi tensor omega for some character on this orbit space. 3, a cuspidal representation, big pi of GL2 of the adels of E, is the base change with respect to E over f of little pi for some cuspidal little pi of GL2 of the adels of f, if and only if, as you might expect, big pi is just invariant under the Galois action. Okay, that one's not too surprising. Where do you go to find a proof of this? Langland's base change for GL2, I believe is the name of the text, is a great place to look here. The proof uses a Galois twisted version of the very, very deep trace formula. And so beginning next video, in fact, the next video will be entirely dedicated to this. We're going to say a little bit about the trace formula. And I would see CNS, Cornell, Silverman, Stevens, page 197 for a sketch of what's going on here. Okay, so I keep lying to everybody. I keep lying to you and telling you we're finally going to get to the proof of this theorem 9 above. Next video, we won't get there. We will have to say a little bit about the trace formula next video. But I absolutely promise that 2 videos from now, we will actually start finally proving this big result, this special case of LRC that we need. Okay, so I'll see you tomorrow, and thanks for watching.